Hello, and welcome to Donaldson Clean Fuel and Lubricant Solutions webinar, Do You Know What Is Plugging Your Filter? This is the 14th in a series of webinars, and several of the topics covered in this one are covered in more detail on our previous series. My name is Jim Doyle. I'm an engineer here with Donaldson Clean Fuel and Lubricant Solutions Group. The objectives for the presentation today are to explain the changes in engine filtration needs, describe the main rapid filter plugging mechanisms found in the field, and describe how diesel fuel users can manage, minimize, or avoid these issues for successful ongoing operation. The crux of the issue with rapid filter plugging being more common now than it was in the past has to do with engine technology development, specifically the fuel injection system. Traditional unit injector equipped diesel engines have a tolerance of particulate larger or smaller than 7 microns. Anything 7 microns, 7 to 10 microns and larger will need to be filtered out, but anything smaller can essentially pass through those injection systems. The modern high-pressure common rail injector system to meet new emissions requirements has a much different tolerance. You see a schematic here of a fuel injector, and there's an area highlighted where the fuel flow is controlled in the engine or into the engine and returned back to the fuel tank. There's a segment in there that has a valve that's under extreme pressure on one side, about 25 to 45,000 psi, and that valve is controlling fuel that either gets injected into the cylinder or returned back to tank. There's an excess of pressurized fuel to ensure that a proper dose of fuel goes into the cylinder each time this injector opens up, and typically on a new engine it's opening about 5 times per cycle. So there's a lot of activity going on there, and that valve opens and closes very quickly, and it opens only very slightly. In an open position, it's a 2 to 3 micron clearance between the two surfaces of the valves. If any particulate gets in between the two surfaces of that valve when it's opening and closing, it begins to impact the seal surface and causes dimpling and eventually erosion. Off to the left here you can see an as-new surface of that valve, and a valve that has seen impacts from very, very fine particulate, and then erosion developed across there, causing leakage across that valve. If flow leakage through that valve increases up roughly 1.5%, the injector will need to be serviced or replaced at great cost in a modern engine. So to get a better idea of what that means to go from a tolerance of particulate 7 to 10 microns and larger, and now to something about 2 to 3 microns and larger, I have depicted here a range of particles, a representation of particles in fuel. Fuel tends to carry very small particles. Anything visible will quickly settle to the bottom of a fuel sample in the bottom of a tank or something. It tends to carry a lot of very fine particles because it's thin and the large stuff settles out. The largest particles, or the smallest particles you can see, are 40 microns and larger. So we're discussing particles here that are much smaller than you can see with the eye. Unless they're at a very high concentration in the fuel, you won't see any difference in the fuel, whether it's as dirty as it can be or very, very clean. It will look almost identical. So here I have depicted a distribution, a representation of the distribution of about 1,000 particles in fuel. There are just a couple of 14 micron and larger particles out of that 1,000. There's maybe 20 or so in the range of 6 to 14 microns and larger. There's about another 30 or so in the 4 microns and larger, 4 to 6 microns and larger size range, totaling about 50 of the 1,000 particles of average size that are distributed in fuel are 4 microns and larger. That means 950 of the particles are below that 4 micron size or in that 2 to 3 micron size range. So if you have an older dispenser filter or an older primary filter on an engine, it's doing a little bit of filtration. It really isn't doing much. It's removing a couple of large particles here and there and maybe a few of the 6 to 14 micron particles, but doing very little else to the vast majority of the particles in the fuel. Those filters tend to last a very long time. Never see them plugging up. You'll see those kind of filters on dispensers and they will last for years and years and never load up because they really aren't removing much in the way of particulate. An older secondary filter, or maybe an older higher efficiency dispenser filter was perhaps a 10 micron nominal filter, and that does a little bit better job. It's removing the 14 micron and larger particles, 2/3 of the 6 to 14 micron particles, maybe half of the 4 to 6 micron particles, and maybe it's starting to grab some of those 4 micron and smaller particles, but not very many. Those filters also tend to last a lot longer, a long time, but they do plug a little bit quicker than a 25. Then we come to the needs of the new modern high pressure common rail engine, and the change in requirement of filtration is dramatic. You need to address almost all of those sub 4 micron particles because they are the ones that can do the damage in that modern high pressure common rail injection system. So the job got much, much bigger. Instead of removing 50 or so of the particles out of 1,000 in a normal fuel supply with an older filter system, you need to remove almost all of those 1,000 particles to maintain proper operation of an injection system. So that change on the filter can from a 7 micron to a less than 4 micron may not seem like much, but that's a huge change in the job a filter must do. Another thing to consider is how much dirt is coming to the filter and what does it look like. And if you get a batch of fuel that, say, has a batch of particles in it, represented here by this depiction of 1,000 particles, and you get another load of fuel and it has its load of particulate in it, that's fine. If you experience a rapid plugging, say you changed your filter and 8 hours later it's plugged, or things were going along fine and all of a sudden the equipment stops very quickly, it's not an increase in more of the same distribution of dirt. Almost always, it's an increase, a massive increase in sub 4 micron particulate, and generally these are associated with chemistry issues or a temperature related issue that's causing a huge increase in that very small particulate. The rest of the particle distribution is still about the same, but you have this enormous change in small particles, which will plug a modern filter, but they don't really bother an older or coarser filter, so they aren't removed there. So to kind of touch on the range of things that plug that we'd like to describe here, here's the range of the typical handful of things we see plugging filters, and I'd like to step through all of those one at a time and discuss the what is going on and then what you can do as a fuel user to remedy the situation and hopefully avoid or minimize it as best you can. First, I'd like to touch on one other aspect of fuel particulate that is actually defined in the specifications. The only true description of fuel generating solids in the fuel standards is in regards to gelling or waxing of fuel. And that has to do with the temperature and the safe operability of the fuel staying liquid at a temperature. It's called the cloud point in general. And the cloud point is the point at which the fuel begins to form solids that make the fuel look cloudy to the naked eye. A few degrees above that, things are starting to come out of solution, but they haven't grown to a size where they start to be visible. You can see here some wax particulate that is generated in fuel. Traditional high sulfur fuel in the old days and straight hydrocarbon fuel can generate flat sheets of wax similar to these, roughly 100 microns in size, and they will load on filters very quickly. A large portion of the fuel compared to the amount of actual dirt in the system will turn into solids due to gelling, and it will overload the filters and plug things very quickly. If you run that fuel or keep that fuel at a temperature above its cloud point, that should be a very minimal issue, but it is a critical parameter to keep in mind when purchasing fuel or using fuel. Know what temperature the fuel will stay liquid at, and make sure your minimum expected operating temperature is above the cloud point by at least several degrees, or you're likely to run into this issue in cold conditions at times. So the first solids formation that isn't really described in standards that causes probably the most frequent unexpected filter plugging issues seen in the field has to do with the use of biodiesel blends and what we refer to as glycerin fallout. Glycerin is a trace contaminant left in the biodiesel when it is manufactured. Most of it is scrubbed out, but there are a couple hundred ppm of glycerin in there, and consider that actual dirt is at about 1 ppm concentration. And even when you blend this biodiesel at different percentages, 5, 10, or 20%, there's still enough of that glycerin in there and in certain conditions, some of it can fall out and make particulate. The image on the left shows a sample of fuel at 100x magnification that has been completely filtered of all hard particulate, but glycerin is starting to come out of solution and leaving, you can see some very small particles in there. The smallest dots you can see on that image are in the, say, the 3 to 4 micron range, and they come out of solution as very small particles. They can stick to any surface, be it pipes or filters, pumps, valves, anything. It will coat all surfaces, but they also tend to stick to each other and agglomerate into larger and larger particles. And on the right side of this slide, you'll see an image that is the same fuel. That's a sample off the bottom of the same tank of fuel. You can see the particles have gotten much larger that have managed to settle down to the bottom. It doesn't take very much of this to plug your filters. As I mentioned, it's usually in the fuel at a concentration much higher than the actual dirt. The conditions that lead to it coming out of solution are decreasing temperature and increase in moisture content in the fuel, and it will lead to dropout and formation of solids that can plug filters. There's 3 images here of very severe glycerin plugging of filters, but typically you see something more like the image on the upper left, and that is the filter looks like a normal used fuel filter. This happens to be off a vehicle, but it is simply greasy to the touch. Glycerin is used in makeup and other things. It's a very greasy material. It would be familiar to lip balm texture, something like that, and it doesn't take very much of it to coat over that surface and plug the filter. Certainly don't expect to see things like these more severe cases, but they do occur occasionally. Solutions for this are to, as I mentioned, keep the fuel warmer than as warm as you can, and keep moisture out of it. The 2 things that are fighting against you are cooling conditions and water. So keeping your tanks clean, and if at all possible, only using biodiesel in warmer conditions to avoid the temperature issue and dropping out solids. That may be the case in certain parts of the country. In northern North America and Canada, biodiesel is not used, but in northern North America, there are states that mandate its use year-round, and there's more frequent use of biodiesel in the southern part of the United States year-round as well. So if a cold snap comes through, you can have conditions that are likely to cause plugging on glycerin. This is probably the most frequent method of filter plugging encountered in the field. The next most common issue we see in the field is something referred to as metalcarboxylates. They're a long-known contaminant in fuel. They have traditionally contributed to injector deposits in older series engines that had coarser filters. As I mentioned a couple times now, very fine particulate will pass through older series engines' filters and just keep continuing on downstream. But with a modern high-pressure common rail engine, secondary filter, or a high-efficiency bulk filter, they will load in that filter. These are not typically generated at end customer sites. This material can be found well upstream, basically all the way to the refinery, and the likely contributors to its formation are present as some of the final steps in finishing fuel at the refinery. It needs water needs to be present, there needs to be some salt present, and the carboxylate portion of the issue is a common chemistry put in fuel as a corrosion inhibitor. So corrosion inhibitor, salt from the final salt bed filtration at the end of the refining process to remove water, and there's some caustic usually used late in the process in fuel manufacture as well. All those contribute to carboxylate formation. Those conditions can but are less likely to occur in tank and storage downstream of the refinery. But regardless, wherever this material forms, it will pass on through coarse filtration until it runs into a high efficiency filter, be it at the bulk dispensing point or a secondary filter on a piece of equipment. It tends to be transitional. There isn't a lot the end user can do to stop it from forming, but you can deal with it better in the bulk position, cleaning fuel up as you take possession of it or before you put it into equipment, and plugging filters there rather than stopping operating equipment. As I said, it tends to be transitional, so it can come and go. It's sort of an upset condition at the refinery that gets remedied, and then the problem will go away. So it shows up, but it will go away generally and only be an occasional incident. You can see the scale bar there is a 10 micron in size. Again, I mentioned that very, very fine particulate is what this is substantially made of. And here's a couple of the larger particles pointed out with those arrows. They're nowhere near as large as the 10 micron scale bar, so they're 5 microns or 6 microns in size. Most of the rest of the small particles you see in that image are all well below that 5 micron size, and they just pass right along until they hit a high efficiency filter. A somewhat related chemistry issue that may be confused in certain analysis with metal carboxylates is something called amine carboxylates. This reaction occurs from the same corrosion inhibitor that's typical in fuel, that's there to prevent damage to pipes and pumps and things. But it's a reaction between that corrosion inhibitor, water, and some amine chemistry that's common in cold flow improver packages, specifically premium cold flow improver packages. And that can form a whole bunch of small solids that will load in filters. And as I said, this is associated with cold flow improver materials that are used only seasonally. So this one is occurring generally further downstream. It's not coming from the refinery. Cold flow improver is usually blended either at the when the tanker truck is being filled up for delivery, or potentially at the end customer site on site there. And if this reaction is occurring, a way to avoid it is to stop using the cold flow improver and perhaps blend some more number 1 to lower your cloud point naturally, or fuel, at least to experiment and see that if this is the cause of the unexpected rapid plugging. Again, this is a seasonal one. You can't address it on fuel coming to you unless you're pre-filtering, and it may be being created at the end customer site. I've mentioned cold flow improver a couple of times here, and I already showed what fuel that was forming solids into large wax crystals looks like. If cold flow improver is in fuel, it tends to try and create crystals of a different shape and size, and that's what improves the ability of the fuel to flow, even though it's at its cloud point and generating particulate. So here is an image of in the upper right of some wax crystals floating around in fuel that's at a temperature where it's starting to form solids. You can see some sort of star-like shapes circled there, and that's called a dendritic crystal. It has sort of a center nucleus and a bunch of spines coming off it, like the sea urchin in the picture there, to give you a better idea of what that looks like in your mind. And the cold flow improver is in there to change that shape of particulate formation. It does not change the temperature that the fuel begins to generate particulate or the amount of particulate it generates. It generates a different size particulate. So in this case, there's a 20 micron scale bar on that image there. You can see these are less than 20 micron particles, which will help the fuel flow through screens and pump down pipes and that kind of thing. But it's still going to load on most of the filters that are used in primary and secondary positions, or even relatively efficient bulk dispensing filters. So it's still forming a solid, it's just a different shape and size, and it's likely to overwhelm filters and plug them quickly. The most robust solution to this is to blend more number 1 diesel fuel and naturally lower the cloud point to a level that when you're going to be operating on your cold fuel, it's still in a liquid state entirely. One additional point, and there's a webinar on this, as I've mentioned on all these topics, we have more extensive detailed webinars on this. Cold flow improver being dosed in at the end use point can lead to additional particulate formation over and above the cloud point, natural cloud point of fuel. If fuel already has cold flow improver in it and you put additional cold flow improver in it, it begins forming particulate at a higher and higher temperature. So always follow the dosing instructions for the cold flow improver and you must be certain whether you have cold flow improver or not in the fuel that you're dosing this into. It's also worth noting that cold flow improver must be put in warm fuel. It cannot be put in fuel that's below about 55 degrees Fahrenheit. It needs to be blended warm for it to function properly. So there are some hazards associated with that, and you must read the instructions to prevent further plugging instead of trying to solve the problem. Now on to what people more normally consider issues with fuels, and that would be dirt or water in your storage tank. And we'll start with a simple depiction of a stationary fuel tank here. You can see this is a clear tank, but you can see at the bottom there's some dirt settled down there and there's some water settled down there. And gravity does a pretty good job of settling those two things out in storage, provided the tank is stationary. That's traditionally been how things are designed and handled for many, many years with diesel fuel. And I've touched a couple of times here where water is a contributor to solids formation, both with glycerin and some of the other additive reactions that create solids. So we don't recommend just letting water build up there. You should do your best to prevent that from building up, and there are some things you can do there. Routine tank cleaning, using desiccant breathers, or perhaps even purging the reservoir headspace with dry air to prevent condensation from building up in there. We have a couple of webinars on that in the set here that are on our website, My Clean Diesel, that you can look at if you have concerns. And then dirt, that can build up in the bottom of the tank, and that as well should be kept at a minimum to avoid certain issues. Again, gravity's doing its job here and settling things out over time, but if you dispense new fuel into that tank and stir things up, or worse yet, you move that tank around. If this is a mobile fueling trailer or a pickup bed tank or a mobile vehicle, and you're not maintaining that tank very clean and dry, as you bump that tank around, you stir things up, and it is possible with a mobile fueling system to dispense far poorer quality fuel out of the nozzle than the fuel you put into that system when you take it down the trail, road, or across the job site and agitate it, shake it up into a milkshake, and dispense it into a piece of equipment. So that needs to be considered. That equipment needs to be held very clean, or you're likely to dispense high concentrations of dirt and get rapid plugging based on that. It's just not a good situation to move dirty fuel around. You'll stir it up and create very unhappy situations with soft solids and hard particles causing you a lot of grief. Lastly, a couple of somewhat unusual but occasional occurring things are salts. I mentioned salts are used in the refining process. They are a drying agent used in the refinery. It's just a large bed of salt, granular salt, that will absorb moisture out of the fuel to get the fuel to a water level low enough to meet specification or be below it, leaving the refinery. Occasionally that tank may allow some salt to migrate out. This is an example of a bulk filter offloading a tanker truck of fuel, and it's loaded up with an awful lot of salt grains that came out of the salt bed at the refining process. Another form it can migrate in, if you look at this scanning electron microscope image here, that's a 1 micron scale bar at the bottom. Those are very, very, very small particles of salt on a secondary filter on a diesel engine, and that has likely come out as salt in water in the fuel, and the fuel dries out when it's warmed and the salt comes out, precipitates out. It's not going to dissolve at all in the fuel and generate very, very fine particulate that will load on filters. So salt can come downstream at some concentration. Obviously the one is big chunks of salt there, and the other is a very low concentration that was collecting over time in a system. But there's not much you can do other than bulk filter and try and prevent that stuff from coming on board in the first place. And it too is a transitional issue. It shows up as a severe issue, and then it will go away because the system has been repaired. And finally, one last material to consider is something called pipeline drag reducer. Seasonally, pipeline drag reducer is used to increase the throughput in distribution down pipelines by as much as 20%. This material is somewhat of in raw form is sort of a fish slime material, and occasionally you will see it show up in fuel that's on the downstream end of a pipeline, and it has not done what it's supposed to do, which is shear in and turn in to become part of the liquid. It will show up as a slimy material. You can see a drip of it hanging from the bottle in that image. That drip hangs all the way over to that 5-gallon pail in the background there. If this is happening, you will see this in a region-wide type of issue. Everybody running on that fuel supply is likely to run into this. This has been seen in on-engine filters, in bulk filters, and again, it's the occasional thing region-wide. You just want to be pre-filtering your fuel at times to catch this kind of thing before it impacts your on-equipment operation. It's not a nice thing to deal with. It can come through filtration at warm temperatures, and in cold conditions drop out as particulate and then lead to plugging, say on the outlet side of a bulk tank that sat through winter or something, or in a piece of equipment that sat over winter in seasonal use conditions. We do see that on occasion. One change of filters or the usage of that fuel, and you'll go back to normal conditions. It's not something necessarily that can be caught on delivery if that fuel is delivered warm. That's the end of our presentation. As I mentioned, each one of these topics has at least one or two related webinars with more detail on how to go about water management and what is glycerin and biodiesel, carboxylate formation, mobile fueling and the hazards of that. We've got several of those topics covered at least in one or more webinars on the website here on My Clean Diesel. And please connect with us today if you haven't already and you found us just on YouTube with this video. The others are all there on My Clean Diesel, along with lots and lots of links to fuel standards and technical articles and troubleshooting guides and that kind of thing. So thank you for your time.